All right. Today we're going to discuss Chapter 10, Section 8, the Taylor and MacLaurin series. So far, what we've seen are geometric series that generate a power series for a function. So we have something like f of x equals 1 over 1 minus x, or f of x equals something like this. So now we're going to look at general functions that represent power series that are infinitely differentiable. So a Taylor series is a function that is infinitely function that is definitely integral and can generate a power series. All right. So here are the questions. If a function has derivatives of all orders on the interval, if a function is differentiable on all points, can it be expressed as a power series on at least one of those intervals? If it can, what are the coefficients? In other words, what it's looking for is this. And goes from 0 to infinity, some coefficient. So as I said, if a function f of x has derivatives of all orders, in other words, does it have a first derivative, second derivative, a third derivative, a fourth derivative, and so on and so forth, can it be expressed as a power series? If so, what are the coefficients? So looking at this, we get a to the 0, a sub 0, anything to 0 is 1, a1 x minus to the power 1, a sub 2, x minus a to the power 2, and so on and so forth, a sub n x to the power a to the power n, push going to infinity. So now we look at the first derivative of these things, of this series. So the derivative of constant disappears. The derivative of this value of x is 1, so it just have a1. Then this one power just 2a2 x minus a to the power 1. Power 3 comes down, so 3a3 x minus a to the power 2, n a n x to the power a n minus 1, and so on and so forth. That's the first derivative. The second derivative, that one disappears. So we have the derivative of this one goes to 0, so it's 2a sub 2 plus 6a sub 3 ax minus a to the power 1, 12a sub 4 x minus a to the squared, and so on and so forth. third derivative. That's a constant, disappears. So we have 6a cubed plus 24a to the fourth, and so on and so forth. Because the other one would be, that's 3 times 4. This was 3 times 4 times 5. 4 times 5 times 6, and so on and so forth. So as this thing goes along, so this is 1 times 2, 1 times 1 times 3, 1 times 2, 1 times 2 times 3, 2 times 3 times 4. That's 3 times 4. Times 2. No, 1 times 2. It's 2 times 3. 3 times 4. 4 times 5. 5 times 6. 1 times 2 times 3. 1 times 2 times 3 times 4. Actually, that's only a series of 3. This is third derivative. So the next one's going to be 3, 4, 5. So that's 60 a sub 5. And then 4 times 5 times 6. What we're looking at is the nth derivative will simply be the n factorial of our nth term. So that's, we can predict those. Let's look at the definitions of Taylor and MacLaurin series. All right. Those two here. All right. Let a function f of x be a function with derivatives of all orders throughout some interval containing a as an interior point in the Taylor series. Generated by the function f at x equals a is this. The summation of k equals 0 to infinity f of k over k factorial times x minus a to the power k. That's the Taylor series. So let's see, and when k is 0, k is 0, that's 1. That's 1. This 0 is no derivative. 0 factorial is 1, so it's just f of a. This is k equals 0. K equals 1. The first derivative, x minus a over 1. X equals 2. 2 factorial, x minus a squared, x to the third, 3 factorial, x minus a to the third, and so on and so forth. And what we get is the nth, which is n factorial, x minus a to the n, and so on and so forth. The MacLaurin series of f is similar to that is a Taylor series generated at x equals 0 or k goes from 0 to infinity, f of k, 0, k factorial, x minus 0, k. Remember, x equals a, that's 0. So at 0, that goes away, that was 1, so it's f of 0. At 1, so it's x over 1. At 2, so it's x squared over 2 factorial. 3 is going to be x cubed over 3 factorial. F4 at 0 is going to be x to the 4th over 4 factorial. F to the n 0, xn over n factorial. Yep. All right, so we see that the MacLaurin series at when a is 0 is the Taylor series, but with a equals 0. Let's look at some examples. Find the Taylor series generated by f of x equals 1 over x at a equals 2. Where, if anywhere, Does the series converge to 1 over x? Since a is 2, we're going to find f2, f prime at 2, f double prime at 2, and so on and so forth. So our function we start off with is f of x equals 1 over x, which is x to the power negative 1. If I take the derivative of this, negative 1 over 2 squared is negative 1/4. The second derivative over 2 squared. So the first derivative is negative x to the negative 2. The derivative of that makes it negative 2, positive 2 over 2. One over x cubed. 1 over 2 cubed. Just 1 over 8. So the derivative of is x negative cubed. Three times 2 times 1 is 6. So it's negative 1/2 x to the 4th. Negative 1/32. So we'll go all the way to so we see that our values alternate signs over 2 to the power n plus 1 because we have that extra 2 on the bottom now. All right. So to find the Taylor series, the way we just figured out, we have f of 2 plus f prime of 2, because a is 2. Hmm. 2 over 3 factorial, x minus 2 cubed, f to the 4th, 2, x minus 2 to the 4th over 4 factorial. all the way to our equation. N minus 2n over n factorial. So that becomes our function f was 1/2. Then we have negative 1/4, negative 1/8. And it changes signs. So it's 1/4 x minus 2 plus 1/8 x minus 2 squared minus 1/32 x minus 2 to the third plus minus negative 1 to the power n x minus 2 to the power n over n factorial. No, 2n minus, sorry, not factorial. This is 2n plus 1 on the bottom. It's always doubling. This one, 16. 16. This series has a common ratio of 1/2. And x minus 2 on top. Negative divided by positive. So we have x minus negative x minus 2 over 4 divided by 1/2 is negative x minus 2. There's x over 2. And the next one's positive and negative. It's be 1/2 on the bottom. Yep. So that's our common ratio is negative x minus 2 over 2. So it is a geometric series. Does it converge or diverge? Since it's alternating series, take the absolute value of it. It's less than the limit, so it's 2a. That's what a is. So convergence absolutely. This sum is r a plus was a function. It's 1 plus x over a. The ratio it was a, the first term. The first term is 1/2 1 plus x plus 2 over 2. One half 2 plus x plus 2 over 2. 1/2 times 2 x plus 4. Two, flip the bottom, so it's 2 over 2 plus 4. It converges to 1 over x. All right, let's look at the next example. No. Next section. Taylor polynomials. We can linearize a polynomial with the initial term this is a degree 1 polynomial. We're using this formula. So f of a plus, this is what we looked at last time. This is when n equals 0. This is when n equals 1. At a. So here's your definition. Let f of x be a function with derivatives of order k equals 1, 2, all the way to n. In some interval containing a as an interior point. And for any integer n from 0 to n, the Taylor polynomial of order n is generated by the function at x equals some value a in the as an interior point. The polynomial p of n f prime of a x minus a. This is when n equals 0, n equals 1, n equals 2. It'll be x minus a squared over 2. This is over 1 factorial. This is over 0 factorial. So f of the third derivative, x minus a to the power 3 over 3 factorial, f to the fourth derivative of a, x minus a to the fourth over 4 factorial, dot, dot, f of n of a, x minus a to the power n over n factorial, and so on and so forth. Oh, order of n, so it stops it there. Now, as I said over here, we use the word order instead of degree because our function to that nth derivative may be 0. So example, f of x equals cosine x at x equals 0. Let's look at the first couple of polynomials, terms of the first two or first three terms of the polynomial, Taylor polynomial. So we have f of a, 0. So cosine of 0 is 1. Cosine of 0 is 1. So it's the term itself is it's well, not excellent 0. So it's we don't even need that. Since the first two terms the derivative of cosine is sine at 0 is 0. So it has degree 0. That's 0. Example 2. Let f be a function with derivatives of order k. K equals 1, 2, all the way up to n. In some interval containing A as an interior point. Then for any integer n from 0 through n, the Taylor polynomial of order n generated by f at x equals a is the polynomial of degree n is f of a plus f prime of a x minus a to the first over 1 factorial, f double prime a x minus a squared over 2 factorial, f triple prime at a is x minus a cubed. Excuse me. And we go all the way to the nth term. X minus a n to n factorial. Find the Taylor series and polynomial generated by f of x equals e to the x at x equals 0. E to the x equals 0. Well, since we know it's since this is always going to equal any derivative. So the first derivative is e to the x, the second derivative, and so on and so forth. So all the derivatives. If that's true, that means all of the terms will equal 1. So this Taylor series is X minus 0 over 2 factorial all the way to f n 0, x minus 0 to the power n factorial. But all these are 1. So I have 1. It's just x, that's 1. X over 2 squared. X squared over 3 all the way to x to the power n over n factorial. Series keeps on going. So we have k factorial on the bottom. And on top, we just have x to the power k. So that's the series. Equals 1 plus x squared over 2, x cubed over 6. The last one will be x to the power n over n factorial. Because polynomial degree n or order n. All right, let's do example 3. The series is an infinite series that goes on from to whatever, but the polynomial, it has an order, so it has to stop at that n value. Okay, find the Taylor series and Taylor polynomial of cosine x at x equals 0. So f of x is cosine x. F prime is derivative of sine is negative sine. The second derivative, sine to negative cosine. And the third derivative is to positive sine. And so on and so forth. F to the fourth derivative is sine to cosine. So f to the power n is negative 1 n cosine x. But it goes in twos, so I have to double it. Does, let's say, okay, let's test this. 3 will be f to the 6 would be negative to 3, 4, 5, 6. It would be a negative value again. So when x equals 0, we get f to the 0 is 1, F prime at 0 is 0. F double prime at 0 is -1. F2 n at 0 is -1 to the power n times 1. Cosine 0 is 1. Two n plus 1 would be -1n. Since we cosine, it'll be 0. So the Taylor series is f of 0 plus f prime at 0 plus, this is x minus a, f of 0 plus f prime of 0, x minus 0, f double prime at 0, x minus 0 squared over 2 factorial. F triple derivative x minus 0 at 3 over 3. Then we just stop there. So we have f2n at 0. This is a 2n. Okay, so the first derivative is 0. And the other one is 0, so it alternates. So we know it's alternating. Just for all the odds. 0, 1, 1 is 0. This n equals 2. So whenever is odd, the derivative is 0. So only keep the even ones. Oh, note. Hmm. No, yeah, just said a second ago, because all the ends are even, all the odd ones we have zeros, so we're only taking with respect to even powers. we figured out that 2n as opposed to 2n plus 1, this one gave us a value. This one was 0. So we notice that the series there for our polynomial so we're going to n in our values. We got cosine of 0 is 1. So it's f of 0 f prime of 0 x 1 factorial f double prime at 0 x squared over 2 factorial 0 x cubed over 3 factorial all the way to negative 1 n x 2n over 2n factorial. Which equals our function is cosine. Cosine of 0 is 1. First derivative of sine, that's 0. The next one is negative cosine, which is negative 1, so it's negative x squared over 2. Zero. So this is n equals 0, n equals 1, n equals 2, n equals 3. So the third derivative is sine, so that's 0. Fourth derivative cosine, so it's x to the 4th over 4 factorial. So equals 1, that was gone, minus x squared over 2 factorial. That one's gone, so it's plus x to the 4th 4 factorial. The next one, so they're alternating. X to the 6 factorial. X to the 8 factorial. So on and so forth. To negative 1n. X to the 2n over 2n factorial. That's the Taylor polynomial. All right, let's see what else we're going to talk about. Okay, example 4 says it's a piecewise defined function. All right, let's do that. Oh, let me go over here. Note. These Taylor polynomials from 0 to infinity. Polynomials go to n. It converges to cosine x as our n goes to infinity. Because the function will always have that one value in it. Example 4. It can be shown that f of x equals 0 when x equals 0, or e to the negative 1 over x squared when x does not equal 0. Okay. It can be shown that f of x has derivatives of all orders at x equals 0, and f of n. It could be shown that the function has derivatives of all orders at x equals 0. Yeah, they're all zeros. And f of n of 0 is 0 for all n. Okay. Examine the Taylor series. So we have f of 0, f prime of 0 x, 1 factorial. F double prime of 0 is x squared over 2 factorial. X cubed over 3 factorial. F of n at 0, x of n over n factorial. So it says when x is 0, f is 0. So f of 0 is 0, 0 times x, 0 times x squared, 0 times x cubed. Zero plus 0 plus 0 equals 0. Converges to 0 for every x. And converges to f of x only at x equals 0. The graph of this. Something like that. All right, let me check something here real quick. All right, well, that's the last example there. So that's the end of the course. Well, I will go through and fix all those videos that I haven't finished yet, or the ones I've lost actually, and the notes as well. So I'll be here for the next 2 weeks. As we can see, for our class, we did Taylor MacLaurin series, and that's it. So you have the rest of the semester to finish your work, catch up, and get all your tests done. Okay, everybody. Good luck. And again, I'll be here on Tuesdays and Thursdays. If you have any questions, just send me a message and I'll respond. All right, take care, everybody. Enjoy the rest of your semester and good luck on your finals.